from high above the earth, where the air thins and the sky turns dark, you can see something remarkable along the edges of every continent. Before we go any further, if you want a brand new Earth topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. There, between the solid ground and the open water, lies a world that belongs fully to neither. It is not quite land. It is not quite lake or river or sea. It is something older, stranger, and more alive than either one alone. These are the wetlands. They stretch across every continent on Earth except Antarctica. They cover roughly 6% of the planet's total land surface. That may sound small, but 6% of Earth is an enormous amount of space. Wetlands span more than 8 million square miles in total. To put that in your mind, picture the entire continent of South America. Now picture it almost completely covered in shallow water, thick mud, tangled roots, and the soft calls of birds you have never heard before. That is closer to the true scale of what wetlands are. A wetland is any place where water covers the soil or sits just below the surface for long enough to change the land itself. The water does not have to be deep. It does not have to be permanent. It just has to stay long enough to shape the ground, the plants, and the creatures that live there. Some wetlands hold water all year. Others flood only in certain seasons, then dry to cracked mud under a summer sun. Both are wetlands. Both are extraordinary. What makes them so special is exactly this in-between nature. They exist at the meeting point of two worlds. The dry land brings one set of plants, one set of animals, one set of rules. The water brings another. Where those two worlds overlap, something new appears. Species that could not survive in the open ocean find shelter here. Species that could not survive in the dry forest find food here. The wetland holds space for both, and in doing so, it becomes one of the most productive places on the entire planet. Scientists measure productivity by how much living material a place can grow in a single year. Wetlands rank among the highest of any ecosystem on Earth. They produce more living matter per acre than most forests. They produce more than most grasslands. Acre for acre, shows more life than almost anywhere else you can stand on this planet. The reason is simple. Wetlands have water, which almost all life needs. They have sunlight reaching shallow depths, and they have rich, dark, nutrient-filled soil built up over thousands of years of slow decay. That combination is almost impossibly generous to life. The ancient world knew this long before scientists had words for ecosystems or biodiversity. Human civilizations built themselves around wetlands. The Mesopotamian marshes of what is now southern Iraq fed some of the earliest cities in human history. The Nile Delta, where the great river spreads out into a wide fan of shallow water and reeds before reaching the sea, was the cradle of Egyptian civilization. The wetlands fed people. They filtered water. They protected coastlines from storms. They gave shelter and food and safety. People have always known on some deep level that these places matter. And yet, for most of recent history, wetlands were treated as wastelands. They were drained, filled, and built over. More than half of the world's wetlands have been lost in the last 100 years alone. That loss happened faster than almost any other large-scale change to the natural world. It happened because people saw standing water and soft ground and thought, useless. It took a long time and a great deal of careful science to understand just how wrong that was. Tonight, we are going to slow down. We are going to move through the wetlands the way the water moves through them, which is gently and without hurry. We will look at the mud beneath our feet and the trees rising out of the water and the birds standing perfectly still in the shallows. We will listen to the frogs and the insects and the deep, quiet pull of a world that has been doing its work for millions of years without asking for any attention at all. The wetlands are patient. They have always been patient, and there is something deeply calming about a place that has no interest in rushing. So let the water rise slowly around you. Let the reeds sway. Let the light go soft and golden. We are just getting started. A wetland is born when water stays. That is the whole secret. Water arrives, and instead of draining away quickly, it lingers. It sits on the ground long enough to change everything about that place. the soil changes, the plants change, the animals that come to live there change, all of it because the water decided to stay. But how does that happen? There are a few different ways, and each one tells its own quiet story. Sometimes the land itself is simply low. Rain falls, and gravity pulls the water downhill, and it collects in a hollow or a basin where there is nowhere left for it to go. Over time, that low spot fills. The soil becomes saturated, which means it is so full of water that it cannot hold anymore. The ground becomes soft and dark and rich. Plants that love wet feet begin to move in. A wetland is born. Sometimes a river does the work. Rivers do not always stay inside their banks. Every year, when snowmelt or heavy rain pushes a river past its edges, the water spills out across the flat land beside it. That flat land is called a floodplain. The water spreads wide and shallow, and when the river pulls back, some of that water stays behind. It soaks into the soil. It fills the low spots. Over hundreds or thousands of years, those floodplains become wetlands, fed again and again by each new flood. The ocean makes wetlands too. Along coastlines all over the world, the tide moves in and out twice a day. It pushes salt water up into low, flat areas near the shore. The plants and animals that live there have learned to handle salt in ways that most living things cannot. These coastal wetlands, called salt marshes and mangrove forests, are some of the most productive places on Earth. They are built by the steady, patient rhythm of the tides. Glaciers also left wetlands behind. Thousands of years ago, enormous sheets of ice covered much of the northern half of the world. When those glaciers melted, they carved hollows and depressions into the land. They left behind uneven ground, full of low spots and ridges. Water collected in those hollows. In places like Canada and the northern United States, millions of small wetlands called prairie potholes formed this way. There are so many of them that from the air, the land looks like it has been dimpled by a giant hand. Scientists estimate there are more than 5 million of these small wetland pockets across North America alone. What all these wetlands share is a single defining quality. The water must be present for at least part of the year, and it must must be shallow. Most wetlands are not deep. In fact, many of the richest and most productive wetlands are only a few inches to a few feet deep. That shallow water is what makes them so alive. Sunlight can reach all the way to the bottom. Plants can root in the mud and still reach the surface. Small creatures can find food and shelter without traveling far. The soil in a wetland is unlike almost any other soil on Earth. Scientists call it hydric soil, which simply means soil that has been shaped by water. When soil stays wet for a long time, the oxygen inside it gets used up. Without oxygen, the normal process of things breaking down slows almost to a stop. Dead leaves, dead plants, dead animals, they do not rot away quickly the way they would in a dry forest. They pile up, they compress, they become a thick, dark, spongy layer called peat. In some wetlands, peat has been building up for thousands of years. There are peat bogs in Ireland and Scotland, where the peat is more than 30 feet deep. 30 feet of slow, quiet accumulation, one thin layer at a time. That peat holds an enormous amount of carbon, the same carbon that plants pulled out of the air while they were alive. Wetlands cover only about 6% of the Earth's land surface, but they hold around 30% of all the carbon stored on land. That is a number worth sitting with. A small fraction of the land, holding nearly a third of the stored carbon. The math alone tells you something important about how much is happening in these quiet, wet places. Every wetland on Earth, whether it was carved by a glacier or built by a river or shaped by the tides, began the same way. Water arrived, water stayed, and the world that grew up around that staying water became something extraordinary, something patient and deep and full of quiet purpose. Not all wetlands look the same. That might seem obvious once you say it out loud, but it is worth slowing down to appreciate just how different these places can be from one another. A swamp in the American South, draped in Spanish moss and thick with the smell of warm mud, looks almost nothing like a cold, flat bog in northern Canada. A tidal marsh along the coast of Georgia, where the grass bends in the salt wind, is a completely different world from a freshwater marsh tucked into the middle of the continent. These places share a name, and they share water, but they were each born in their own way, shaped by their own forces over their own stretches of time. Scientists sort wetlands into 4 main types. There are marshes, swamps, bogs, and fens. Each one has its own character, its own chemistry, its own community of living things. Marshes are dominated by soft plants, things like cattails and reeds and grasses that grow up through shallow, still water. You have likely seen a marsh at the edge of a lake or along a slow river. The plants stand tall and close together, their roots underwater, their green stalks reaching toward the sky. Marshes are some of the most productive places on Earth, meaning they grow more living material per acre than almost any other type of land. Swamps are different. Where a marsh is soft and grassy, a swamp is woody. Swamps are wetlands where trees and shrubs take over. The bald cypress trees of the American Southeast grow right out of the water. Their wide, flared bases anchoring them in the soft mud. The water beneath them is dark and still, stained a deep amber color by the tannins, the natural chemicals that leach out of decaying leaves. Walking into a cypress swamp feels like stepping into another century. The light filters down through the canopy in long, pale shafts. The air is heavy and warm. Everything moves slowly, if it moves at all. Bogs are something else entirely. A bog forms in a place where water collects, but has almost nowhere to drain. Rain falls, fills a hollow in the land, and stays. Over time, a thick mat of sphagnum moss, a soft, spongy plant that can hold up to 20 times its own weight in water, spreads across the surface. Sphagnum moss is remarkable. As it grows, it releases acids into the water. The bog becomes more and more acidic over time, until very few bacteria can survive there. Without bacteria to break things down, dead plants and animals are preserved almost perfectly. Bogs have given us ancient human bodies, some more than 2,000 years old, with their skin and hair and clothing still intact. The cold, acidic water of the bog held them as carefully as any museum. Fens are close cousins to bogs, but with one key difference. A fen receives water not just from rain, but from groundwater and streams that flow in from the surrounding land. That incoming water carries minerals, which makes fens less acidic than bogs. Fens support a wider variety of plants, including grasses, sedges, and wildflowers. They are often found in cool northern regions, spread across parts of Canada, Siberia, and northern Europe, where the ground stays wet for most of the year. Each of these 4 types was born from a different set of conditions. A bog needed a hollow and a cold climate and time. A coastal marsh needed tides and sediment, and the slow work of grasses building land from water. A cypress swamp needed a river that flooded regularly, depositing rich soil across a flat plain year after year. None of these places appeared overnight. They each took shape across decades or centuries, or in some cases thousands of years, as water and soil and living things worked on each other in a slow, patient negotiation. What is striking is that all of this variety grew from the same basic starting point. Water arrived and stayed. That single condition, water staying in place long enough to change everything around it, produced some of the most diverse and productive places on the planet. The same force that built a cold, silent bog in Finland also built a warm, tangled swamp in Louisiana. The same patient accumulation of water and time. The same willingness of the land to hold what the sky sent down. Each type of wetland is its own world, and yet they are all expressions of the same deep tendency in nature, the tendency of water to gather, to linger, and to transform whatever it touches into something richer than it was before. Beneath every wetland, beneath the still water and the tangled roots and the quiet surface, there is ground. And that ground tells a story older than anything living above it. Start with the mud. Wetland mud is not ordinary dirt. It is a dense, dark mixture of clay particles, decomposing plant matter, and water that has been pressed together over long stretches of time. When you step into it, it holds you. It pulls at your boot. That grip is real. The tiny clay particles in wetland soil carry a slight electrical charge, and they cling to each other and to anything that touches them. Scientists call this kind of waterlogged Oxygen-poor soil, hydric soil, meaning soil shaped entirely by water. It is darker than upland soil. It smells faintly of sulfur, and it is extraordinarily rich. The darkness comes from carbon. Wetland plants grow quickly in warm seasons, pulling carbon from the air through their leaves. When they die and fall into the water, they do not fully decay the way a fallen leaf would on dry forest ground. There is not enough oxygen in waterlogged soil for the tiny organisms that break down dead material to do their work completely. So the plant matter builds up, layer by layer, season by season. It accumulates into a soft, spongy material called peat. Peat is essentially a slow-motion record of every plant that ever lived and died in that wetland, compressed into the earth. Peat builds slowly. In many bogs, it grows at a rate of about 1 millimeter per year. That is roughly the thickness of a fingernail. A peat deposit 3 meters deep, which is not unusual, could represent 3,000 years of continuous plant growth and accumulation. Some peat deposits in the far north are far older than that. Scientists have found peat layers in Siberia and Canada that began forming more than 10,000 years ago, just after the last great ice sheets pulled back from the land. That connection to the Ice Age is worth sitting with for a moment. The peat beneath a quiet northern bog began forming when woolly mammoths still walked the earth. The ground itself is a kind of archive, holding the chemistry and the carbon of a world that no longer exists above the surface. The carbon stored in peat is staggering in its scale. Wetlands cover only about 6% of Earth's land surface. Yet, they hold roughly 30% of all the carbon stored in the world's soils. The world's peatlands alone store more carbon than all the world's forests combined. That carbon arrived in the wetland the same way it always does, drawn out of the air by green leaves, built into stems and roots, and then locked into the ground when those plants died in oxygen-poor water. The wetland did not plan this. It simply created the conditions where carbon could not escape. Now consider where that carbon came from in the first place. Every carbon atom in a piece of peat was once floating in the atmosphere as carbon dioxide. before that, it may have been locked inside a rock, slowly released by volcanic activity over millions of years. And before that, the carbon itself was forged inside a star. Carbon is not made on Earth. It is made in the nuclear furnaces at the hearts of massive stars, built from lighter elements under enormous heat and pressure. When those stars died and scattered their material across space, that carbon drifted through the galaxy for billions of years before becoming part of a young solar system, then a young planet, then the air, then a leaf, then a root, then the soft, dark peat beneath a marsh in Louisiana or a bog in Ireland. The mud holds all of that history without knowing it. There are gases in the mud too. As organic material breaks down in the low oxygen environment of wetland soil, microbes produce methane, a colorless gas that sometimes bubbles up through the water in small, silent puffs. You can see this on still days in a quiet swamp. Tiny bubbles rising from the bottom and breaking the surface. Those bubbles are ancient carbon, briefly returning to the air after centuries underground. Iron is there as well. Wetland soils often show streaks of orange and gray, where iron compounds shift between different chemical states, depending on how much water and oxygen are present. The same iron that colors wetland mud was also forged in dying stars. The same process that built the iron at Earth's core. It traveled here across unimaginable distances and unimaginable time. And now it sits quietly in the mud at the bottom of a swamp, tinting the water a faint amber gold. The ground beneath a wetland is not empty or inert. It is full of history, full of chemistry, full of carbon and iron and ancient time. All of it held gently in place by water that decided long ago to stay. Look at the surface of a wetland on a calm morning. It seems like nothing is happening. The water is flat and still. A few insects skate across it. A heron stands motionless at the edge. Everything looks quiet, almost frozen in place. But just beneath that still surface, forces are constantly at work. Invisible, patient, and powerful. Water is heavy. A single cubic foot of water weighs about 62 pounds. When water fills a wetland, it presses down on everything below it with enormous, steady weight. That pressure shapes the soil. It compresses the peat. It pushes gases and dissolved minerals sideways through the ground, moving them slowly from one place to another. The weight of the water above is one of the quiet engines that drives everything happening below. Gravity pulls that water downward always. In a wetland, the ground is saturated, meaning it is completely full of water, like a sponge that cannot hold another drop. Because of this, water cannot sink much deeper. It has nowhere to go, so it spreads outward instead, creeping slowly across flat land, filling every low spot, every hollow, every slight depression in the earth. Wetlands often form in places where the land is nearly level, because gravity spreads the water wide rather than letting it drain away fast. The flatness and the water work together, each one reinforcing the other. Beneath the waterlogged soil, something else is happening. Heat from the earth below moves upward very slowly. The way warmth rises from a stone that has been sitting in the sun. This geothermal heat, the steady warmth that radiates from the planet's interior, is gentle in most wetlands. It is not dramatic, not volcanic, but it is constant. It keeps the soil from freezing solid in winter in many places, allowing microbial life to continue working even through cold months. Those microbes, tiny living things too small to see, are the real workers of the wetland. They break down dead plant material. They cycle nutrients. They produce gases. And they do all of this because the temperature stays just warm enough to keep them going. Oxygen, or the lack of it, is one of the most powerful forces shaping a wetland. In a normal forest soil, air moves freely through the ground. Oxygen reaches deep into the earth. But in a wetland, water fills all the spaces between soil particles, pushing the air out. The result is an anaerobic environment, a place with very little oxygen. This changes everything. Decomposition slows dramatically. Carbon builds up instead of escaping. Different kinds of microbes take over, ones that can survive without oxygen, and they process the organic material in different ways, releasing methane instead of carbon dioxide. The absence of one simple gas reshapes the entire chemistry of the place. place. Tides shape many wetlands near coastlines. Twice a day, in tidal marshes and mangrove swamps, the sea pushes inland. Salt water floods the roots of the plants. Then it retreats. This daily rhythm of flooding and draining is a force as regular as a heartbeat. It brings nutrients in from the ocean. It carries sediment, the fine particles of sand and silt that settle out of the water and slowly build up the floor of the marsh. Over decades, this sediment accumulates. The marsh grows upward, very slowly, keeping pace with the sea. Scientists have found that healthy tidal wetlands can build themselves up at roughly the same rate that sea levels rise. A kind of quiet biological engineering that has been going on for thousands of years. Even the moon plays a role. The moon's gravity pulls on the oceans, creating tides. Those tides push into coastal wetlands. So the same force that lifts the sea toward the sky twice a day also floods the roots of marsh grasses and mangrove trees. The moon and the swamp are connected by gravity across nearly 250,000 miles of space. Sunlight drives the whole system from above. It warms the water. It powers the plants. It drives evaporation, pulling water upward from the surface and releasing it into the air as invisible vapor. On a warm day, a large wetland can release enormous amounts of water into the atmosphere this way. That moisture rises, cools, and eventually falls again as rain, sometimes far away. The wetland breathes water into the sky, and the sky returns it somewhere to the earth. Still water, quiet surface, but underneath and above and all around, gravity and pressure and heat and oxygen and tides and sunlight are all pushing and pulling, shaping this place every single moment. The stillness is not emptiness. It is the calm face of something that never stops working. Now think about the plants that live in all that pushing and pulling. Think about what it takes to survive with your feet underwater, sometimes for months at a time. Most plants would simply drown. Their roots need oxygen, just like we do. Soil that sits underwater for too long becomes airless and dark, and ordinary roots suffocate in it. But the plants of the wetland have found a way around this problem, and the solution they found is one of the most quietly remarkable things in the plant world. Some wetland plants grow special roots that reach up instead of down. They push out of the mud and rise above the waterline, poking into the open air like snorkels. These are called pneumatophores, which simply means air carriers. Mangrove trees are famous for them. Walk through a mangrove forest at low tide, and you will see hundreds of these pale, finger-shaped roots jutting up from the mud in every direction, some just a few inches tall, some rising nearly as high as your knee. They look almost like the mud itself is breathing, and in a way, it is. Each of those roots has tiny pores on its surface. Air enters through those pores and travels down into the root system below the mud, carrying oxygen to the parts of the plant that cannot reach the surface. The tree has built its own ventilation system, running through its own body, stretching from the open air down into the airless dark below. A single large mangrove tree can have hundreds of these breathing roots surrounding it, spreading outward from the trunk in a wide circle. If you stood in the center of that circle and looked out, the roots would surround you like a quiet crowd. Now think about the scale of this. The Sundarbans, the vast mangrove forest shared by India and Bangladesh, covers roughly 4,000 square miles. That is larger than the state of Delaware and Rhode Island combined. Within that forest, the mangrove roots form a structure so dense and so tangled that it is nearly impossible to walk through. Scientists estimate the root systems in a healthy mangrove forest can hold the soil together with a grip strong enough to resist the force of a powerful storm surge. The wall of water that a hurricane pushes ahead of itself onto shore. Those small, pale, finger-shaped roots collectively can slow a wave. Cypress trees solve the same problem differently. In the swamps of the American South, bald cypress trees grow what are called knees. These are rounded, woody bumps that rise up from the roots and poke above the waterline. A big cypress tree can have dozens of these knees surrounding it, some shaped like rounded cones, some twisted and strange, rising a foot or two out of the dark water. Scientists still debate exactly how they work, but the leading idea is that they help the tree breathe in flooded conditions, much like the mangroves snorkel roots stand in a cypress swamp in the early morning, with mist sitting low on the water and those knees rising out of the stillness. And the place feels ancient. It is ancient. Some bald cypress trees alive today began growing more than 1,000 years ago. Consider that for a moment. A tree that was already old when the first European explorers reached North America. A tree that has been breathing through its knees, season after season, flood after flood, for longer than most nations have existed. The oldest known living bald cypress in the United States stands in North Carolina, in a swamp called Black River. Scientists have measured its age at over 2,600 years old. That tree was already centuries old when the Roman Empire was at its height. It has survived droughts and floods and storms and the slow creep of changing climate. It still stands. It still breathes, and it is not alone. The Black River Swamp contains dozens of trees over 1,000 years old. The whole forest is a quiet record of time, written in wood and water. This is part of what makes wetlands so hard to truly picture. The scale is not just about size, though the Sundarbans alone could swallow 2 small states. The scale is also about time. These places are old in a way that is hard to hold in your mind. The roots have been breathing for centuries. The mud beneath them holds thousands of years of fallen leaves and slow decay. The trees have watched the world change around them and simply kept growing, kept reaching upward, kept sending air down into the dark. Roots that breathe, trees that remember, a forest that holds back the sea. Close your eyes for a moment and picture a swamp forest, not from the edge, but from inside it. You are standing in shallow, still water. It comes up just past your ankles. The surface around you is dark, almost black, reflecting the pale sky above in broken pieces between the leaves. The air smells of wet earth and green growing things. And all around you, rising up from the water like quiet giants, are the trees. Swamp trees are unlike any trees you might find in a dry forest. They have had to solve a problem that most trees never face. Their roots sit in soil that is soaked through, sometimes completely underwater for months at a time. Waterlogged soil holds very little oxygen, and roots, like all living things, need oxygen to survive. So swamp trees have found their own slow solutions, each one shaped by millions of years of living in the wet. The bald cypress, which we have already met, is one of the most recognizable. But look closely at the base of a cypress tree, and you will see something strange and wonderful. The trunk does not simply rise straight from the water. It swells outward near the bottom, flaring wide like the base of a cathedral column. This wide, fluted base helps the tree stay upright in soft, unstable mud. It acts like a broad foot, spreading the tree's weight across the soggy ground so it does not tip or sink. The wood at the base is dense and strong, a deep reddish brown, almost the color of old brick. Around the base of a cypress, the knees rise up from the water. These pale, smooth wooden cones glow softly in the dim light of the swamp. Some are just a few inches tall. Others reach as high as a person's waist. Scientists still study exactly how these structures work, and evidence suggests they help the tree exchange gases with the air above the waterline, getting oxygen down to the submerged roots below. A grove of cypress knees looks like something from a quiet dream. Dozens of pale shapes standing in dark water, perfectly still. The black tupelo tree is another swamp dweller, and it shares the cypress's talent for patience. Tupelo wood is famously tough and twisted, with fibers that spiral through the grain in ways that make it nearly impossible to split. This dense, interlocking wood helps the tree resist the twisting forces of floodwater. In autumn, the tupelo's leaves turn a deep, burning red, one of the most vivid colors in any wetland. A stand of tupelo in October looks like it is on fire, reflected in the still black water below. In the swamps of the American South, the water tupelo grows with its base permanently submerged. Its trunk swells into a wide, bottle-shaped base, sometimes several feet across, tapering up into a more slender form above the waterline. This bottle shape gives the tree extra buoyancy and stability in the soft mud. From above, a flooded tupelo swamp looks like a forest of dark bottles standing in a mirror. Further south, In the coastal swamps of Florida and the Caribbean, the red mangrove takes over. The red mangrove grows its own kind of knees, called prop roots, which arch down from the trunk and branches like curved stilts, plunging into the water and anchoring the tree in place. A single red mangrove can send dozens of these arching roots downward, creating a dense tangle below the waterline. From a boat, you look into a mangrove forest and see a world of curved wooden arches disappearing into dark water. The whole structure holding the tree up like a living scaffold. The leaves of swamp trees tend to be broad and waxy, built to handle both intense sun and long periods of shade when the canopy closes in above. Many are a deep, glossy green, catching what light filters down through the branches. Hanging mosses, especially Spanish moss in the American South, drape from the branches in long silver-gray curtains. Spanish moss is not actually a moss at all. It is a flowering plant, a relative of the pineapple, that pulls moisture and nutrients directly from the air. It does not harm the trees it hangs from. It simply rests there, softening the whole forest into something that looks like a painting of itself. Stand in a swamp forest and look upward. The canopy above is a patchwork of green and gray and silver, broken by strips of pale sky. The light that reaches you is soft and filtered, like light through frosted glass. Everything is muted. Everything is still. The trees around you have been solving the same problems for millions of years, and they have done it quietly, slowly, without hurry. They are still working on it now. Below the trees, below the roots, below the dark water itself, another world begins. Most people think of a swamp as what they can see: the gnarled trunks, the hanging moss, the still brown surface of the water. But the surface is only the beginning. Beneath it lies a hidden structure, layer by layer, that is just as complex and just as alive as anything above. Start at the water's surface. Floating there in patches of green and gold are the plants that live between two worlds. They are rooted in the mud far below, but their leaves rest flat on the water, open to the sky. The water lily is the most famous of these. Its round, waxy leaves, called lily pads, can stretch more than a foot across in some species. The giant water lily of the Amazon, Victoria amazonica, grows pads that reach nearly 10 feet wide. A small child could sit on one without sinking. The underside of each pad is ribbed like the frame of an umbrella, a structure that spreads the weight and keeps the leaf rigid. These plants have been floating on warm, shallow water for a very long time. Fossil relatives of the water lily date back more than 90 million years to the age of the dinosaurs. The flowers of the water lily open and close with the light. Many species open in the morning and close by afternoon. Some open only at night, pale and glowing in the dark water, drawing in moths and beetles to carry their pollen. The flower produces heat as it opens, a process called thermogenesis, which helps spread its scent into the cool night air. The warmth attracts insects the way a lamp attracts them. It is a quiet trick, ancient and effective. Below the lily pads, the stems reach down through the water column, sometimes several feet, anchoring the leaf to the mud. These stems are hollow. They carry oxygen down from the air above into the roots buried in the airless mud below. The plant breathes through its leaves and feeds its own roots through these long, thin tubes. It is a private pipeline running silently between the sky and the deep mud. Other floating plants have no roots at all. Duckweed is one of the smallest flowering plants on Earth. Each individual plant is a single tiny oval, barely the size of a match head, with one thin root hanging down into the water. Duckweed covers the surface of still wetland water in dense green mats, sometimes turning entire ponds a solid, vivid green. It doubles in number roughly every 2 days under good conditions. A single pond can go from clear to completely covered in a matter of weeks. Beneath that green carpet, the water is shaded and cool. Insects and small fish shelter there, hidden from birds above. Deeper still, beneath the floating plants and the open water, the mud begins. Wetland mud is not ordinary mud. It is thick, dark, and rich with organic matter. The broken down remains of every plant and animal that has ever lived and died in that water. This layer is called the benthic zone, the bottom layer of any body of water, and wetland, it is one of the most productive places on the planet. Bacteria work constantly in this mud, breaking down dead material and releasing nutrients back into the water. Those nutrients rise slowly upward, feeding the plants above, which feed the insects and fish, which feed the birds. The whole system runs on what the mud gives back. The mud also holds seeds. Wetland mud can contain thousands of dormant seeds per square foot. Seeds that have been waiting, sometimes for decades, for the right conditions to sprout. Scientists call this the seed bank. If a wetland is drained and then reflooded years later, plants can return from seeds that have been buried and waiting the entire time. The wetland remembers what it was. It carries its own future in the ground. Some of those seeds belong to plants that have not grown in that spot for a generation. Others belong to species that are rare or struggling elsewhere. The mud holds them in reserve, patient and still, until the water comes back. Look down into the dark water of a swamp, and you see very little. The water is stained brown by tannins, natural compounds released by decaying leaves, the same compounds that color a cup of tea. The light fades quickly. A foot below the surface, it is already dim. 2 feet down, it is nearly dark. But life does not stop where the light does. It simply changes, adapts, and continues, layer by layer, all the way down to the waiting mud below. And yet, even in that dim and tannin-stained water, something is always moving. The shallows of a wetland are one of the most alive places on Earth. Not loud about it, not obvious, but alive in every direction, at every depth, at every hour of the day. The creatures here do not wander in from somewhere else. They belong to this place completely. Their bodies are shaped by it. Their rhythms follow its rhythms. They rise and fall with the water, with the seasons, with the slow turning of the year. Frogs are among the oldest residents of the wetland world. They have been here in one form or another for more than 250 million years, long before the first dinosaur walked the earth. Frogs were already calling from the edges of ancient pools. The wetland gave them everything they needed: shallow water for their eggs, mud to burrow into during cold months, single frog can eat thousands of insects in a season. They are quiet, patient hunters, and the swamp suits them perfectly. Frogs do not simply live in wetlands. They measure them. Scientists use frog populations as an indicator species, meaning a species whose health tells us about the health of the whole system around it. When frogs are thriving, the wetland is usually thriving too. When frog numbers drop, it is often a sign that something in the water or the air has shifted. They are sensitive to changes in temperature, water quality, and chemistry in ways that make them a kind of living alarm system for the ecosystem. The cycle of a frog's life is the cycle of the wetland itself, written small. In spring, as water warms and daylight stretches longer, frogs emerge from the mud where they have spent the winter in a state of deep stillness. They call from the reeds and the shallows. The sound of a wetland in early spring is largely the sound of frogs, a chorus that can carry for miles on a quiet night. Females lay their eggs in clusters or long strings of jelly attached to submerged stems. The eggs hatch into tadpoles. The tadpoles breathe water through gills. Then, over weeks, something remarkable happens. The tadpoles transform. They grow legs. They absorb their tails. Their gills close and lungs open. They crawl out of the water and onto land. The same animal that once breathed water now breathes air. Few changes in nature are that complete. Turtles follow a different rhythm, slower and older. Many wetland turtles live for decades. Some painted turtles, a common species across North American wetlands, can live for more than 40 years. They spend their days basking on logs in the sun, warming their bodies, since they cannot generate their own heat the way mammals do. On cold days, they sink to the bottom and slow nearly to a stop. Their metabolism drops so low that they can survive winter underwater without breathing air at all. They absorb just enough oxygen through their skin to keep going. They wait, still as stones, until the warmth returns. Turtles are important to wetlands in ways that are easy to overlook. They eat algae, aquatic plants, insects, and small fish. They keep populations in balance. Their movement through the water stirs up nutrients from the bottom. When they dig nests in the soil at the wetland's edge. They aerate the ground. Even their shells, when they eventually die, become habitat. Small invertebrates, the tiny creatures without backbones, move in and make use of what remains. Those invertebrates are everywhere in the shallows. Dragonfly larvae cling to submerged stems for months, sometimes years, before they climb out of the water and split open their own skin to emerge as adults. Water striders walk on the surface tension of the water, their weight spread across 6 legs so evenly that they never break through. Crayfish move backward through the mud, scavenging whatever they find. Aquatic beetles carry a bubble of air beneath their wings so they can breathe while diving. Each one is a small solution to the problem of living in a place that is neither fully water nor fully land. This is the pulse of the shallows. Not one creature, but thousands, each following its own cycle, each connected to the others. The frog eats the insect. The turtle eats the frog's eggs. The heron eats the turtle's hatchlings. The dead heron feeds the mud. The mud feeds the plant. The plant shelters the frog. Around and around, season after season, the shallows keep their quiet, steady rhythm, patient as the water itself. Above all of that quiet activity in the shallows, something moves. A shadow crosses the water. Long legs fold and extend. A great blue heron lands at the edge of the marsh with barely a sound, settling its gray-blue body into perfect stillness. It stands there like a statue carved from patience. And then, in a single strike too fast for the eye to follow, it drives its long beak into the water and pulls out a fish. The great blue heron is one of the largest wading birds in North America. It can stand nearly 4 feet tall. Its wingspan stretches to almost 6 feet across, and yet it moves through the wetland with a kind of quiet grace that seems impossible for something so large. It hunts by waiting. It watches the water with sharp yellow eyes, reading every ripple, every shadow. When it strikes, it uses its beak like a spear. It swallows fish whole, head first, so the fins fold flat on the way down. Herons are not alone in the wetland sky. Egrets wade nearby, their white feathers bright against the dark water. The great egret, dressed entirely in white, uses the same slow hunting method as the heron. During breeding season, long feathery plumes grow from its back, trailing behind it like soft ribbons. These plumes were once so prized by hat makers that egrets were hunted nearly to extinction in the early 1900s. Their recovery, thanks to early conservation laws, is one of the quiet success stories of the natural world. Smaller birds work the edges. The snowy egret, much smaller than its great cousin, actually stirs the water with its bright yellow feet to startle prey into moving. It is one of the few birds known to use this active hunting trick. The tricolored heron dashes and pivots through the shallows, chasing fish rather than waiting for them. Each species has found its own way to live in the same place without competing too directly with the others. They share the wetland by dividing it up, each one claiming a slightly different depth, a slightly different method, a slightly different time of day. Then there are the birds that hunt from above. The osprey, a large hawk built almost entirely for fishing, hovers over open water and then drops feet first into the surface, sometimes plunging completely underwater to grab a fish in its curved talons. Its outer toe can rotate backward, giving it 2 toes in front and 2 behind, which helps it grip a slippery fish in flight. The bottoms of its feet are covered in tiny spines for the same reason. Everything about the osprey is shaped by the wetland. The wetland shaped the bird, and the bird helps shape the wetland by moving nutrients from the water to the land when it carries fish to its nest. Ducks and geese rest on the open water in great numbers. Mallards tip forward to feed on underwater plants, their tails pointing straight up at the sky. Pintails, with their long, elegant tail feathers, do the same. Canada geese graze on marsh grasses at the water's edge, their honking calls carrying across the open water in the early morning. These birds are not just visitors. They are part of the wetland system. Their droppings add nitrogen to the water, feeding the algae and the plants. Their feet carry seeds from one wetland to another, spreading plant life across distances no wind could manage. The purple gallinule walks across lily pads on enormous feet. Its body, a startling mix of purple, blue, and green that that seems too vivid for a bird living in a muddy swamp. Its long toes spread its weight across the floating leaves, so it never sinks. The roseate spoonbill wades through shallow water, swinging its flat, spoon-shaped bill from side to side, filtering small creatures from the water as it walks. Its pink color comes entirely from the shrimp and other small crustaceans it eats. Without the wetland's food, the spoonbill would fade to white. Kingfishers perch on low branches over the water, watching below with a stillness that rivals the heron. When they spot a fish, they dive headfirst. A small blue and orange streak hitting the surface and returning almost instantly with prey in their bill. They nest in tunnels they dig into riverbanks, sometimes 3 feet deep into the earth. All of these birds, from the towering heron to the tiny kingfisher, depend on the wetland completely. And the wetland depends on them. They carry seeds. They move nutrients. They control fish populations. They are not separate from the water and the mud and the reeds. They are woven into it, each one a working part of something far larger than itself. When the sun drops below the tree line and the last light fades from the water, the wetland does not go quiet. It shifts. A whole new world wakes up, and the marsh becomes something different entirely. The first sound you notice is the frogs. On a warm summer night near a healthy marsh, the noise can reach 90 decibels. That is as loud as a lawnmower running a few feet away. Some species of tree frog can be heard from a mile away on a still night. They call to find mates, and they call in waves, one group starting and another answering. So the whole marsh seems to pulse with sound. Scientists have found that frogs time their calls to avoid overlapping with other species. Each one finds its own gap in the noise. The result is a kind of layered chorus, every voice fitting into the space left by another. The firefly is one of the marsh's most remarkable nighttime residents. These small beetles produce light through a chemical reaction inside their bodies, a process called bioluminescence. No heat comes from that light at all. Nearly all of the energy goes directly into the glow, making it one of the most efficient light sources in the natural world. Some species of firefly in the Great Smoky Mountains synchronize their flashes, thousands of them blinking in unison across the dark water and grass. Scientists believe they do this to help females identify males of their own species. On a still night over a wetland meadow, the effect looks like slow, soft lightning trapped just above the ground. Moths replace butterflies after dark, and the wetland feeds them well. Some wetland moths have wingspans of nearly 6 inches. They navigate by the stars and the moon, using the angle of light to hold a straight path across open water. When artificial lights were introduced near wetlands, many moth populations began to decline. They circle artificial lights endlessly, burning energy and never finding food or mates. The wetland at night is built for natural darkness, and even small changes to that darkness ripple through the whole system. Bats arrive as the light fades. A single little brown bat can eat up to 1,000 mosquitoes in 1 hour. Wetlands produce enormous numbers of insects, and bats have followed that food source for millions of years. They navigate using echolocation, sending out pulses of sound too high for human ears to hear, and listening for the echo that bounces back from a flying insect. The time between the call and the echo tells them exactly how far away the prey is. Some bats can detect an object no wider than a human hair using only sound. Over a marsh on a warm night, dozens of bats may be hunting at once, each one tracing invisible arcs through the dark air above the reeds. The otter is one of the wetland's most active nighttime hunters. River otters can hold their breath for up to 8 minutes and dive to depths of 60 feet. They hunt fish, crayfish, and frogs, and they are fast enough to catch fish in open water. Their fur traps a layer of air against their skin, keeping them warm even in cold water. Otters are playful animals, and scientists have observed them sliding down muddy banks repeatedly, not to travel, but apparently for the pleasure of it. They are among the few non-human animals that seem to engage in play as adults. The marsh at night belongs most completely to the owl. The barn owl can locate prey in total darkness using sound alone. Its face is shaped like a dish, and that shape funnels sound toward its ears the way a satellite dish collects a signal. Its ears are set at slightly different heights on its skull, which lets it calculate the exact position of a sound in 3 dimensions. A barn owl can hear a mouse moving under 6 inches of snow over a wetland where small rodents move through the reeds and grasses. The owl is the most precise hunter alive. All of these creatures, the calling frogs, the flashing beetles, the hunting bats, the diving otters, the silent owls, are not simply using the wetland as a backdrop. They are part of how it functions. Bats control insect populations. Otters keep fish numbers in balance. Owls hold down the rodents that would otherwise eat too much of the marsh grass. Even the frogs, by eating insects and being eaten by herons and snakes, move energy from one part of the system to another. The wetland at night is not resting. It is working quietly and completely under a sky full of stars. And when the sun finally rises over the marsh, the night shift gives way to something older, much older. Reptiles have lived in wetlands for an almost impossible stretch of time. Crocodilians, the group that includes crocodiles, alligators, and their close relatives, have existed for more than 200 million years. They watched the dinosaurs rise. They watched the dinosaurs fall. And they are still here, sliding silently through the same kind of warm, shallow water their ancestors knew long before humans walked the earth. There is something quietly astonishing about that. The swamp has been their home across a span of time our minds can barely hold. The American alligator lives across the wetlands of the southeastern United States, from the cypress swamps of Florida to the slow bayous of Louisiana. An adult male can grow to 11 feet long and weigh more than 500 pounds. But for all that size, the alligator moves through water with almost no sound. It holds its body just below the surface, with only its eyes and the top of its snout showing above the waterline. From a distance, it can look like a floating log. That stillness is not laziness. It is patience, perfected over millions of years. The alligator's eyes sit on top of its head, and this placement is no accident. It lets the animal see above the surface, while its body stays hidden below. Behind each eye is something called a tapetum lucidum, a reflective layer that bounces light back through the eye a second time. This is the same structure that makes a cat's eyes glow in the dark. At night, if a light shines across a wetland, you can sometimes see dozens of small orange-red glows scattered across the water. Each one is a pair of alligator eyes watching. Alligators are also one of the few reptiles that build nests and guard their young. A female alligator gathers mud, leaves, and plant matter into a mound that can be 6 feet wide and 3 feet tall. She lays her eggs inside and then stays close, sometimes for weeks, protecting the nest from predators. When the eggs are ready to hatch, the babies make high-pitched calls from inside the shell. The mother hears them and carefully opens the nest. She may even carry the hatchlings gently in her mouth, down to the water's edge. For an animal often seen as cold and distant, this is a striking kind of care. The temperature inside the nest determines whether the eggs become male or female. This is called temperature-dependent sex determination, and it means the weather itself shapes the next generation. Warmer nests tend to produce more males. Cooler nests tend to produce more females. Scientists are watching this closely because as global temperatures rise, the balance between male and female alligators in some populations may begin to shift. Alligators also shape the wetland in ways that go far beyond their own survival. During dry seasons, alligators dig out depressions in the mud with their bodies and tails. These are called alligator holes, and they hold water long after the surrounding marsh has dried out. Fish, turtles, birds, and insects all gather at these holes to survive the dry months. When the rains return and the water spreads back across the land, those animals spread with it, reseeding the wetland with life. The alligator, without any intention of doing so, keeps the whole system alive. Turtles are another ancient presence in the swamp. The snapping turtle, with its rough shell and powerful jaw, has a body plan that has changed very little in tens of millions of years. It spends most of its life on the muddy bottom of slow-moving water, almost invisible. It eats fish, frogs, insects, and plant matter. And in doing so, it moves nutrients from one part of the wetland to another. When it crawls out to bath, bask on a log in the afternoon sun. It is warming its body to help digest its food. Since reptiles rely on outside heat rather than generating their own warmth from within, water snakes glide through the shallows, hunting frogs and small fish. Skinks and small lizards move through the grasses at the water's edge. Each of these animals carries hundreds of millions of years of history in its body. They are not relics. They are proof that the wetland as a place has been worth living in for an almost unthinkable length of time. The swamp did not just welcome these creatures, it shaped them, and they in turn shaped the swamp. That exchange has been going on since long before the first flower bloomed or the first bird sang. It continues quietly every single day. Long before the reptiles arrived, and long before the first flower opened, the insects were already here. They were here before the swamp had a name. They were here before any human eye had ever looked across a stretch of still, dark water and wondered what lived beneath it. And when people finally did begin to study wetlands with care and patience, it was the insects that surprised them most. For most of human history, swamps were places to avoid. Ancient cultures across Europe and Asia believed that swamps caused illness. They were right, in a way, though not for the reasons they thought. People believed that the bad air rising from still water was itself the source of disease. The word malaria comes from old Italian words meaning bad air. For centuries, that was the explanation. The smell was real. The sickness was real. But the cause was invisible. It took until the late 1800s for scientists to understand what was actually happening. A British doctor named Ronald Ross, working in India in 1897, made a careful and patient study of mosquitoes. He was not the first to suspect them, but he was the first to prove it. He dissected mosquitoes under a microscope and found the tiny parasite that causes malaria living inside the insect's body. That discovery changed medicine forever. It also changed how people thought about wetlands. The swamp was not poisoning people with its air. A small, delicate insect was carrying something far more dangerous than any smell. Mosquitoes breed in still, shallow water. Wetlands provide exactly that. A single female mosquito can lay hundreds of eggs at a time, and those eggs can hatch in just a few days. Scientists studying wetland mosquito populations in the early 20th century were stunned by the numbers. In some marshes, the density of mosquitoes in summer could reach tens of thousands per acre. That discovery led to decades of effort to drain and destroy wetlands, especially in the United States, where large-scale drainage projects reshaped millions of acres of marsh and swamp. It seemed, at the time, like progress, but as those wetlands disappeared, researchers began to notice something troubling. The mosquito populations did not always go down, and other things did go down, things that mattered. Fish populations fell, bird populations fell, flooding got worse in areas that had once been protected by the slow absorption of water through marsh soil. Scientists began to look more carefully at what had actually been lost. And what they found, piece by piece, was that the insects they had feared were only one small part of a much larger and more careful system. Dragonflies, for example, eat mosquitoes. A single dragonfly can consume hundreds of mosquitoes in a single day. Dragonflies have been flying over wetlands for more than 300 million years, which makes them among the oldest flying insects on Earth. Early naturalists who studied dragonfly behavior in the 1800s noticed that they always stayed close to water. It took more careful study to understand why. Dragonflies lay their eggs in or near water, and their young, called nymphs, live entirely underwater for months or even years before becoming the fast, shimmering flyers we see above the surface. Those nymphs are fierce hunters. They eat mosquito larvae, small worms, and even tiny fish. When researchers in the 20th century began mapping the food chains of wetland ecosystems, they found dragonfly nymphs sitting near the center of a web of connections that touched almost every other creature in the water. Remove the dragonfly, and the mosquito population could explode. Remove the mosquito, and the bats and birds that feed on them would have less to eat. Every thread pulled at another. Water beetles were another discovery that changed how scientists understood wetlands. Some species can carry a small bubble of air beneath their wings, allowing them to breathe while fully submerged. Early entomologists, the scientists who study insects, were fascinated by this. It seemed almost impossible. A creature that carries its own air supply into the water, hunts underwater, and then flies away when it needs to move to a new pond. These beetles were studied closely in the 1800s and early 1900s, and what researchers found was that they moved between wetlands, carrying nutrients, bacteria, and even the eggs of other creatures on their bodies. They were connectors, living bridges between isolated pools of water. The more scientists looked, the more they found. Caddisflies build tiny cases out of sand and sticks to protect their soft bodies while they develop underwater. Mayflies emerge in such vast numbers that their swarms can be seen on weather radar. Each discovery added another layer of understanding. The insects were not a problem to be solved. They were the engine. They had been running the show all along, quietly, invisibly, in the water and the air above it, since long before anyone thought to look. Fish. Most people picture fish in rivers, in lakes, in the open ocean with its vast blue distances. A flooded forest seems like the wrong place entirely. Too dark, too tangled, too full of roots and fallen branches and slow, murky water. But fish have been living in flooded forests for millions of years, and some of them have found ways to thrive there that seem almost too strange to believe. The Amazon River basin floods every single year. When the wet season arrives, the river rises dramatically, sometimes by as much as 30 to 40 feet. The water spreads out across the surrounding forest, flooding an area roughly the size of England. This flooded forest is called the várzea, a Portuguese word that simply means floodplain forest. For several months each year, the trees stand in deep water, and the fish swim between them. Scientists were surprised to find that hundreds of fish species actively seek out this flooded forest. They do not avoid it. They depend on it. The tambaqui, a large silver and black fish that can weigh over 60 pounds, swims through the treetops during flood season. It eats fruit, actual fruit that falls from the branches above. The tambaqui has strong, flat teeth, almost like molars, built for cracking open, hard seeds. It waits beneath fruiting trees, the way a person might wait beneath an apple tree in autumn. Researchers studying the Amazon found that some trees have evolved to produce seeds that float, making them easier for fish to find. The trees and the fish have shaped each other over millions of years. This relationship has a name. Scientists call it ichthyology, which means seed dispersal by fish. The fish eat the fruit, swim away, and later pass the seeds in a different part of the forest. They are planting trees. A fish moving through a flooded forest is doing the same work as a bird carrying a seed in its beak. The forest depends on the flood. The flood brings the fish. The fish plant the seeds, and the seeds grow into the trees that will one day drop their fruit into the next flood. Some fish in flooded wetlands have developed abilities that seem to belong to a different kind of animal entirely. The lungfish, found in African and South American wetlands, can breathe air. It has a lung, not just gills. When the dry season arrives and the water disappears, the lungfish burrows into the mud. It surrounds itself in a cocoon of mucus, a thick, slippery substance its body produces, and it waits. It can survive in this state for months, even years, breathing slowly through its lung, while the world above dries out and bakes in the sun. When the rains return and the water rises, the lungfish wakes up. It has been doing this for an extraordinarily long time. Fossils of lungfish look almost identical to the living animals we find today. They have barely changed in 300 million years. The walking catfish is another creature that breaks the expected rules. Found in the wetlands of Southeast Asia and parts of Florida, where it arrived as an introduced species. This fish can move across dry land. It uses its pectoral fins, the fins just behind its head, to push itself forward. It can breathe air for short periods using a special organ above its gills. When one pond dries up, the walking catfish simply walks to another one. People who have seen this for the first time often do not believe what they are looking at. A fish moving across a road, heading for the next patch of water. Even in the still, oxygen-poor water of a deep swamp, fish have found solutions. The bowfin, a thick-bodied fish native to North American wetlands can gulp air at the surface when the water around it becomes too low in oxygen. Many wetland fish tolerate conditions that would kill fish from cleaner, faster-moving water. They have adapted to the murk, the warmth, the tangle of roots. They have made a home in a place that most creatures pass by. What all of this reveals is something quietly astonishing. The flooded forest is not a disruption to the lives of these fish. It is the whole point. The flood is the season they have been waiting for. The rising water is a signal that food is available, that it is time to move, to eat, to reproduce. The swamp, which can look from the outside like a place of stillness and decay, is for these fish a place of abundance, a place they return to season after season, the way a person returns to somewhere they have always felt at home. There is another kind of wetland that holds memory, the way still water holds a reflection. It is called a peat bog, and what it preserves is almost beyond belief. A peat bog forms in cool, wet climates where a particular kind of moss, called sphagnum moss, grows in thick, spongy mats across the surface of shallow water. Sphagnum moss is extraordinary. It can hold up to 20 times its own weight in water. When you press a handful of it, water streams out like a wrung cloth. It blankets the ground in soft, pale green cushions, and beneath those cushions, something slow and remarkable is happening. When sphagnum moss dies, it does not fully decay. The bog is too wet, too cold, and too low in oxygen for the usual process of rot to take hold. Instead, the dead moss compresses. It presses down on the layers beneath it. Over hundreds and then thousands of years, those compressed layers become peat, a dark, dense, spongy material made almost entirely of ancient plant matter. In some bogs, the peat is many meters deep. Scientists have found peat layers that began forming more than 10,000 years ago, not long after the last great ice age ended. This is where the bog becomes something more than a wetland. It becomes a record, because decay is so slow inside a peat bog. The things that fall into it are often preserved with stunning detail. Pollen from ancient forests drifts into bogs and sinks into the peat, thousands of years. Scientists can drill down through the layers and pull up core samples, long cylinders of peat that read like pages in a book. Each layer holds the pollen of the plants that were alive when that layer formed. By studying those pollen grains under a microscope, researchers can reconstruct what the forests and grasslands of ancient Europe or North America looked like. Century by century, going back further than any written record. The bog remembers what the land used to be, and it preserves more than pollen. Peat bogs across northern Europe have yielded something far more startling: human bodies. These are called bog bodies, and they are among the most haunting discoveries in all of archaeology. The cold, acidic, oxygen-poor water of a peat bog can preserve soft tissue, skin, hair, and even the contents of a person's last meal for thousands of years. The Toland man, found in Denmark in 1950, had been placed in a bog around 400 BCE. His face was so well preserved that the workers who found him thought they had stumbled onto a recent crime. He looked as though he had simply lain down and closed his eyes. Scientists determined he had eaten a meal of porridge and seeds before he died. The bog had kept that detail safe across more than 2,000 years. This is the connection that makes peat bogs so astonishing. They are not separate from the history of the land around them. They are its memory. The forests that grew nearby shed their pollen into the bog. The animals and people who lived at the water's edge sometimes fell in or were placed there. The climate shifts of entire geological eras left their marks in the chemistry of the peat. A bog is a place where time slows down so much that the past and the present exist side by side. The same sphagnum moss that makes a bog feel soft and quiet underfoot is also the reason that record survives. Its chemistry creates an environment so acidic and so low in the nutrients that bacteria need to thrive that the usual forces of decomposition simply cannot get a foothold. The moss, by being what it is, accidentally becomes a guardian of everything that enters the water. This connects to something larger. Every system in the natural world produces effects that ripple outward in ways that were never planned. The moss does not intend to preserve the past. The bog does not choose to record the climate, but the conditions they create together. The cold, the acid, the stillness, the depth produce something that scientists now depend on to understand how the Earth has changed over thousands of years. Ice cores from glaciers do something similar. So do tree rings. So do the layered sediments at the bottom of ancient lakes. The Earth keeps its own records, written in materials that most people would never think to read. The Peat Bog is one of the quietest places on Earth. It sits low and dark beneath an open sky. The surface trembles slightly when you walk on it. And somewhere beneath your feet, pressed into the dark, is a world that has not changed since long before anyone was alive to see it. Wetlands do something that most people never think about. They clean water, not with filters or chemicals or machines. They clean it slowly, quietly, the way only a living system can. When water flows into a wetland, it does not rush through. It spreads out. It slows down. The plants and the mud and the tangled roots create a kind of maze, and the water has no choice but to move gently through all of it. That slowness is everything. As the water moves through, something remarkable happens. The soil and the roots and the tiny living things in the mud pull out the harmful substances that the water is carrying. Nitrogen and phosphorus, the chemicals that wash off farm fields and lawns and city streets, get absorbed by wetland plants before they can reach rivers and lakes. This is why scientists sometimes call wetlands the kidneys of the earth. Kidneys filter the blood. Wetlands filter the water. The comparison is almost perfect. A single acre of wetland can remove thousands of pounds of nitrogen from the water each year. That is not a small thing. Nitrogen sounds harmless, but too much of it in a lake or a river causes algae, the green plant-like growth that floats on the surface, to multiply out of control. When algae blooms this way, it blocks sunlight from reaching the water below. Fish and other creatures suffocate. The whole system collapses. Wetlands stand between that collapse and the clean, open water that rivers and lakes are supposed to be. This filtering work has been going on for a very long time. long before there were farms or cities or roads. Wetlands were still cleaning the water that moved through them. Rain would fall on ancient forests and plains, pick up minerals and sediment as it ran downhill, and eventually pass through a marsh or a swamp before reaching a river. The wetland would take what it needed and let the cleaner water through. The rivers that fed ancient civilizations were partly kept clean by the wetlands that lined their banks. But the world has changed. Over the last few centuries, and especially in the last 100 years, wetlands have been drained, filled, and built over at a speed the earth has never seen before. People wanted flat, dry land for farms and towns. Wetlands were seen as wasted space, as places that were good for nothing except mosquitoes and mud. So they were removed. Ditches were dug. Water was redirected. The land was dried out and put to other uses. More than half of the world's wetlands have disappeared since the 1700s. In some parts of the world, the number is even higher. The United States alone has lost more than half of the wetlands it once had. Europe has lost even more. These losses happened gradually, one drained marsh at a time, one filled swamp at a time. Each individual change seemed small. Together, they added up to something enormous. And as the wetlands disappeared, the water got worse. Rivers and lakes that had once been cleaned by the marshes around them began to carry more pollution. Algae blooms became more common. Drinking water became harder to treat. Scientists began to understand what had been lost, not just in terms of wildlife, but in terms of the invisible work that wetlands had been doing all along. The good news is that this understanding has changed how many people think about these places. Wetland protection laws began to appear in the second half of the 20th century. In the United States, the Clean Water Act of 1972 gave wetlands a new kind of legal standing. Destroying a wetland without permission became much harder. Other countries followed with their own protections. Restoration efforts began as well. People started putting water back into drained marshes. They replanted native grasses and sedges along riverbanks. They broke apart the old drainage ditches and let the land flood again. Slowly, carefully, the wetlands began to return. The plants came back first, then the insects, then the birds, then the fish. Life, given even a small opening, tends to fill it. What this shows is something the earth has always known. Systems that are damaged can recover if they are given time and the right conditions. The wetland does not need much help. It needs water, and it needs to be left alone. Given those two things, it will do the rest itself. The roots will spread. The mud will deepen. The water will slow. And the quiet, patient work of cleaning and filtering and holding will begin again, just as it always has, just as it was always meant to. That quiet, patient work of holding is perhaps the most powerful thing a wetland does. And to understand it fully, you have to think about light. Specifically, the light that pours down after a heavy rain. The light that glitters on a swollen river. The light that reflects off a flooded field, silver and wide, stretching toward the horizon. That light is telling you something. It is showing you water that has nowhere else to go. And the wetland, sitting quietly at the edge of things, is the reason so much of that water never reaches your door. When a storm rolls in and rain hammers the ground, water moves fast. It rushes off rooftops and roads and hard-packed soil. It pours into streams and rivers, filling them quickly. Without anything to slow it down, that water becomes a flood. It rises, it spreads, it destroys. But when a wetland sits between the storm and the town, something different happens. The water flows into the marsh, into the swamp, into the bog. And there it slows. The thick tangle of roots and stems and waterlogged soil acts like a giant sponge, soaking up enormous amounts of water and holding it in place. Scientists have measured this effect carefully. A single acre of wetland can hold up to 1.5 million gallons of water. That is roughly the size of 2 Olympic swimming pools, absorbed into the ground and the plants and the standing pools of a single wetland acre. In a large marsh or swamp, that number multiplies fast. The Atchafalaya Basin in Louisiana, one of the largest wetland systems in North America, can hold back billions of gallons of floodwater from the Mississippi River. Without it, the flooding downstream would be far far worse than anything seen today. The light on a wetland after a storm has a particular quality. It comes through low and golden, catching the mist that rises off the water. The surface of the marsh glows. Droplets cling to cattail stems and sedge blades, each one catching the light like a tiny lamp. The water level is visibly higher than it was the day before. You can see the high water mark on the trunks of cypress trees, a dark ring of wet bark a foot or two above the current surface. The wetland has done its work. It has taken the storm's fury and absorbed it quietly, without drama. This flood protection is not just about holding water in place. It is also about releasing it slowly. A wetland does not keep water forever. Over days and weeks, it lets that stored water seep gradually back into the ground, or release it gently into nearby streams. This slow release keeps rivers from spiking dangerously after storms. It spreads the water out over time, turning what could have been a destructive surge into a steady, manageable flow. Hydrologists, the scientists who study how water moves through the land, call this function peak flow reduction. The wetland shaves the top off the flood. Coastal wetlands do something even more remarkable. When a hurricane or tropical storm pushes a wall of water toward shore, that surge of seawater can be catastrophic. But salt marshes and mangrove forests along the coast act as buffers. Every mile of healthy coastal wetland can reduce storm surge height by as much as 1 foot. In a major storm, that difference can mean the gap between a flooded street and a flooded living room. The mangroves, with their dense, arching roots, break the force of the waves. The marsh grasses bend, but do not break. The water loses energy as it moves through them, arriving at the shore quieter and lower than it would have been. After Hurricane Katrina struck the Gulf Coast in 2005, researchers looked carefully at which areas suffered the most damage. The places with intact wetlands nearby fared better than the places where wetlands had been drained or filled. The data was clear. The wetlands that remained had softened the blow. The ones that were gone had left the land exposed. There is something deeply moving about this. The wetland does not know it is protecting anyone. It is simply being what it is, The roots grow because that is what roots do. The soil absorbs water because that is what saturated soil does. The grasses bend in the surge because that is what grasses do. And yet the result is a kind of shelter, a living shield built from mud and roots and still water, standing between the storm and the shore. The light after the rain finds all of this. It catches the wet leaves and the gleaming water surface and the high water marks on the old cypress trunks. It shows you what happened here. It shows you what was held. Beneath all of that held water, beneath the bent grasses and the old cypress roots and the dark still surface of the swamp, something else is being held, something invisible, something that has been quietly accumulating for thousands of years, pressed down into the mud, locked away in the peat, stored in a silence so deep you could almost hear it if you listened. That something is carbon. Wetlands store carbon the way a vault stores gold. They take it in, press it down, and keep it. The process is slow and steady and ancient. When plants grow in a wetland, they pull carbon dioxide out of the air. This is what all plants do. But in a wetland, when those plants die, something different happens. The waterlogged soil has very little oxygen in it. Without oxygen, the dead plant matter cannot fully break down. It does not rot away the way a fallen leaf rots on dry ground. Instead, it sinks. It compresses. It becomes peat, that dense, dark layer of half-decomposed plant material that builds up over centuries, over millennia, holding the carbon inside it like a secret. Scientists estimate that peatlands alone store roughly twice as much carbon as all the world's forests combined. Let that image settle for a moment. All the great forests of the earth, the Amazon, the boreal forests of Canada and Russia, the ancient woodlands of Southeast Asia, all of them together hold less carbon than the quiet, unassuming bogs and fens and waterlogged soils of the world's wetlands. The carbon is not in the trees you can see. It is in the ground you cannot. And the sound of all this, if you could hear it, would be a deep and patient hum. Not dramatic, not loud, more like the low resonance of something enormous breathing very slowly. Wetlands do not rush. They accumulate. They hold. The The sound of carbon being stored is the sound of stillness itself. But there is another sound too, a softer one, the sound of methane rising through the water in small bubbles, breaking the surface with a faint, almost imperceptible pop. Wetlands also produce methane, a greenhouse gas, as part of the natural process of decomposition happening in their oxygen-poor depths. This is not a flaw. It is simply part of how these systems work. Wetlands both store carbon and release small amounts of methane. Scientists study this balance carefully because the net effect across most of the world's wetlands is still one of carbon storage. The wetland takes in more than it gives back. The trouble comes when wetlands are drained. When the water is removed, oxygen rushes into the soil. The peat, which had been locked away and preserved for thousands of years, suddenly begins to decompose. The carbon that had been held so patiently begins to release. A drained peatland can become a source of carbon dioxide rather than a store of it. The vault, once opened, empties quickly compared to how long it took to fill. Indonesia holds some of the world's deepest and most carbon-rich peatlands. In some places, the peat is more than 10 meters deep. That is roughly 3 stories of compressed, ancient plant matter, built up over 10,000 years or more. When fires sweep through drained Indonesian peatlands, as they have in recent decades, the burning peat releases enormous amounts of carbon dioxide into the atmosphere. The smoke from these fires has at times blanketed entire regions of Southeast Asia. The sound of that burning is the sound of thousands of years of stored time releasing all at once. This is why scientists and conservationists speak about wetlands with such urgency. Protecting a wetland is not only protecting the birds and the fish and the dragonflies and the water lilies. It is protecting a carbon store that took longer to build than any human civilization has existed. It is keeping the vault closed. There is something almost musical about this when you step back far enough to hear the whole composition. The wetland breathes in. It holds. The plants grow and die and sink and compress. The water keeps the oxygen out. The carbon stays. Year after year, century after century, the mud grows a little deeper, the peat a little thicker, store a little larger. The wetland does not know it is doing any of this. It is simply following the rules of water and soil and time. And yet the result is one of the most important functions any ecosystem on Earth performs. The quiet mud at the bottom of a swamp may be doing more to steady our climate than almost anything else on the planet. All of it happening in the dark. All of it happening in the deep, patient silence below the still water's surface. Wetlands do not just store the past, they also shape what comes next. There is a kind of math happening above the water's surface that is just as quiet and just as powerful as what happens in the mud below. It moves through the air. It touches the clouds. It bends the path of rain. And it all begins with something as simple as water turning into vapor. Every wetland releases moisture into the air above it. This process is called evapotranspiration, the combined release of water from both the wet soil and the living plants. A plant pulls water up through its roots and releases it through tiny pores in its leaves. The wet ground sends moisture upward on its own. Together, a large wetland can push enormous amounts of water vapor into the sky every single day. Scientists have measured this effect carefully. A healthy wetland can release hundreds of thousands of liters of water into the atmosphere each day, depending on its size and the temperature of the air. That vapor does not disappear. It rises, cools, and forms clouds. Those clouds carry moisture across the land. Some of it falls as rain, sometimes hundreds of miles away. This means a wetland in one place can water a forest or a field in another. The connection is invisible, but it is real. Water that soaks into a marsh in the morning may fall as rain on a distant hillside by the following week. The wetland is not just a place where water collects. It is a place where water is sent back out into the world. This is one reason scientists pay close attention to the numbers. Researchers have found that in some regions, wetlands contribute a measurable share of the local rainfall. In parts of the Amazon basin, where vast flooded forests stretch for thousands of kilometers, the wetland system helps generate a phenomenon scientists call a flying river. a stream of water vapor moving through the atmosphere that carries as much water as the Amazon River itself carries on the ground. The math behind this is staggering. The Amazon River moves roughly 15 trillion liters of water into the ocean every single day. The flying river above it moves a similar amount through the sky. Two rivers, one wet and one invisible, running side by side. Temperature is part of this story too. A wetland stays cooler than the dry land around it. The water absorbs heat during the day and releases it slowly at night. This smooths out the temperature swings that dry land experiences. A field bakes in the afternoon sun and freezes on a clear night. A wetland nearby holds its temperature more steadily over a large enough area. This effect changes the local climate in ways that farmers and ecologists have both noticed. The presence of water buffers the extremes. There is an elegant ratio hiding inside all of this. Scientists who study wetland hydrology, the movement and behavior of water, have found that wetlands return roughly 50 to 90% of the precipitation they receive back into the atmosphere through evapotranspiration. The exact number depends on the type of wetland, the season, and the climate, but the range itself is remarkable. A wetland is not a dead end for water. It is a relay station. Water arrives, soaks in, feeds the plants, rises through the leaves, and returns to the sky. The cycle continues without pause. Wind patterns feel this too. Moist air behaves differently than dry air. It is slightly lighter, and it moves differently across the surface of the land. Large wetland regions can influence where storm systems travel and how much rain they carry. The Florida Everglades, for example, play a role in the moisture patterns of the entire southeastern United States. Drain the Everglades, and you do not just lose the birds and the alligators and the sawgrass. You shift the math of the atmosphere above a continent. The numbers behind wetlands and weather are not cold or abstract. They describe something warm and alive. They describe water climbing through the stem of a cattail and drifting upward into a blue sky. They describe a cloud forming over a marsh and traveling west to water a grove of trees that has never seen the swamp that fed it. they describe temperature curves that flatten out around the edges of a lake, giving the frogs and the herons and the turtles a steadier, gentler world to live in. The wetland breathes out, and the sky answers. The sky answers, and the rain falls somewhere new. The rain falls, and the roots drink, and the vapor rises again. The numbers are elegant because the system they describe is elegant. Simple rules followed faithfully, producing something vast and alive and deeply connected to everything around it. There are wetlands on every continent on Earth except Antarctica. They exist at the equator and near the poles. They sit at sea level and high in the mountains. Each one is different. Each one is irreplaceable. And together, they form one of the most important living networks our planet has ever built. The Pantanal spreads across the heart of South America, covering parts of Brazil, Bolivia, and Paraguay. It is the largest tropical wetland in the world. At its peak flood season, water covers an area roughly the size of France. The Pantanal holds more than 650 species of birds, 90 species of mammals, and over 260 types of fish. Jaguars walk its muddy banks. Giant river otters slip through its dark channels. Capybaras graze at the water's edge in the long golden light of late afternoon. The Pantanal is not a quiet place. It hums and calls and splashes with life at every hour. Far to the north, the boreal peatlands of Canada and Russia stretch across millions of square miles. These are the great cold wetlands of the world. They are not lush or tropical. They are slow and ancient and still. The sphagnum moss that blankets them grows only a millimeter or two each year. But over thousands of years, that moss has built up layers of peat dozens of feet deep. Scientists estimate that these northern peatlands store more carbon than all the world's tropical forests combined. They are cold vaults, holding the past in place, keeping ancient carbon locked away from the sky. The Okavango Delta in Botswana is one of the most unusual wetlands on Earth. Most rivers flow toward the ocean. The Okavango does not. It flows inland, spreading out across the flat sands of the Kalahari Desert and forming a vast inland delta where there should be nothing but dust and heat. The water arrives each year in Angola. It travels slowly down the river, taking months to arrive. When it does, the desert blooms. Elephants wade through the shallows. Hippos rest in the cool channels. Thousands of birds descend on the sudden green. Then, slowly, the water soaks into the sand and evaporates into the dry air, and the desert returns. The Okavango is a gift that arrives once a year and then quietly disappears. In Southeast Asia, the Mekong River Basin supports some of the most productive freshwater wetlands on the planet. The Tonle Sap Lake in Cambodia actually reverses its flow with the seasons. During the dry season, the lake drains south into the Mekong. But when the monsoon rains arrive and the Mekong rises, the river pushes back, forcing water upstream and flooding the lake until it grows to 5 times its dry season size. This reversal happens every year, like a slow breath in and out. The flooded forests around the lake become nurseries for fish. Hundreds of millions of people across Southeast Asia depend on those fish as their main source of food and income. The Sundarbans, shared between India and Bangladesh, form the largest mangrove forest in the world. They sit at the mouth of the Ganges and Brahmaputra rivers, where fresh water and salt water meet in a tangle of roots and tidal channels. The Sundarbans protect the coastline from cyclones. They filter the water flowing out to sea. They are home to the Bengal tiger, which has learned to swim between islands and hunt in the flooded forest. The whole system balances on the edge of salt and fresh, land and sea, calm and storm. It is a place that should not work, and yet it does, with remarkable precision. What all these places share is a kind of fragility that is easy to miss from a distance. The Pantanal depends on seasonal floods that follow ancient patterns. The Okavango depends on rains falling in the right place at the right time. The Sundarbans depend on the rivers, continuing to carry the right amount of silt and fresh water to the coast. Change one piece, and the whole system shifts. Drain a river upstream, and the delta begins to shrink. Warm the climate, and the snowmelt arrives too early, throwing off the timing that every creature in the wetland has built its life around. These great wetlands have survived ice ages and shifting continents. have outlasted the dinosaurs. They have absorbed floods and droughts and centuries of change. But they survived because the conditions around them remained within certain limits. The balance held. And as long as the balance holds, these ancient, water-soaked places continue to do what they have always done. They breathe, they filter, they shelter, they endure. But the balance does not always hold. Right now, wetlands are disappearing faster than almost any other place on Earth. Scientists estimate that since the year 1700, more than a third of the world's wetlands have been lost. Some estimates put the number closer to half. The exact figure is hard to pin down because, for most of human history, no one was keeping careful count. That uncertainty itself tells a story. We have been draining and filling these places for so long that we lost track before we even understood what we were losing. The reasons are not mysterious. Wetlands sit on flat, low ground near water. That is exactly where people want to build farms and cities. Across Europe and North America, vast stretches of marsh and bog were drained over the past few centuries to create farmland. The rich, dark soil that builds up in wetlands over thousands of years is extraordinarily fertile. Farmers knew this. And so the draining began, long before anyone understood what those wetlands were doing for the surrounding land and water and air. What we still do not fully understand is how much we lost when they went. This is one of the open questions that keeps wetland scientists up at night. Every wetland is different. Every one holds a slightly different mix of plants, animals, water chemistry, and soil history. When a wetland disappears, it takes that specific combination with it. Scientists are still working to understand how much of that knowledge, that biological record, is simply gone. The peat bogs of Ireland and Scotland, for example, hold thousands of years of climate data locked inside their layers. But many of those bogs have been cut for fuel or drained for farming. The record is incomplete. Pages are missing from a book that took 10,000 years to write. There is another mystery that scientists are actively working on. Wetlands, as we have seen, store enormous amounts of carbon in their soils. But when a wetland is drained, that carbon does not stay put. The peat dries out. It begins to break down. And as it breaks down, it releases carbon dioxide and methane into the air. Methane is a greenhouse gas, a gas that traps heat in the atmosphere. That is far more powerful than carbon dioxide over short time periods. Scientists know this happens. What they are still trying to measure precisely is how much gas is released, how fast, and whether restoring a drained wetland can reverse that release. The numbers are large. Drained peatlands alone may be responsible for nearly 5% of all human-caused greenhouse gas emissions each year. That is a significant amount from a place most people never think about. The restoration question is one of the most exciting frontiers in earth science today. When a wetland is damaged, can it come back? And if it comes back, does it come back the same? Evidence suggests that wetlands can recover, sometimes with remarkable speed. Reintroduce the water, and the plants begin to return. The plants bring insects. The insects bring birds. Within a few decades, a drained field can begin to look and function like a wetland again. But scientists are still learning how deep that recovery goes. Does the soil rebuild its carbon stores? Do the same species return, or different ones? Does a restored wetland filter water and buffer floods, as well as an ancient one? These questions do not yet have complete answers. There is also the question of what wetlands we have not yet found. Beneath the surface of tropical forests, hidden in remote mountain valleys, buried under Arctic permafrost, the permanently frozen ground of the far north, there are almost certainly wetland systems that have never been studied. Satellite imaging has revealed pockets of standing water and saturated soil in places that no researcher has ever visited on foot. Each one of those places might hold species unknown to science. It might hold climate records, or water filtering systems, or breeding grounds for animals we have not yet described. The world is still full of wet, quiet, undiscovered places. And that is something worth sitting with for a moment. After centuries of exploration, after satellites and sonar and deep-sea cameras, there are still corners of this planet doing their quiet, essential work in near total anonymity. Wetlands are not dramatic. They do not announce themselves. They do not roar like volcanoes or tower like mountains. They simply sit at the edge of things, filtering and storing and sheltering, asking nothing in return. The fact that we are still learning how much they matter, still discovering how many of them exist, still trying to understand what happens when they are gone, is not a failure of science. It is a reminder that the earth is still teaching us, and we are still slowly learning to listen. Close your eyes for a moment and imagine standing at the edge of a swamp just before dawn. The air is thick and warm. The water is perfectly still. And then, slowly, the world begins to speak. A frog calls from somewhere in the reeds. Then another answers. Then a third from further away. Within minutes, the whole marsh is alive with sound. Frogs are among the oldest living voices on this planet. Their ancestors were calling across ancient swamps more than 250 million years ago, long before the first dinosaur ever walked the earth. The sounds you hear at the edge of a wetland today are, in a very real sense, some of the oldest sounds life has ever made. The chorus frog, a small gray-brown creature no bigger than a thumb, produces a call that sounds like a finger dragged across the teeth of a comb. It is a simple sound, but it carries far across open water. Male frogs call to attract mates, and the females of many species choose their partners based on the strength and rhythm of that call. The wetland itself shapes the sound. Open water reflects it. Dense reeds muffle it. The marsh is not just a home for these animals. It is their concert hall. Wetlands are among the loudest places on Earth at certain times of year. During spring breeding season in North America, the combined calls of frogs, toads, and insects can reach 90 decibels, which is roughly as loud as a lawnmower. Scientists actually use sound recordings to monitor the health of wetland ecosystems. A healthy marsh has a complex, layered soundscape. Many different species calling at different pitches and rhythms, overlapping without drowning each other out. When a wetland is stressed or degraded, that complexity collapses. Fewer species call. The sound becomes thin and flat. Researchers call this acoustic ecology, the study of what a place sounds like as a way of measuring its health. Birds add their own layer to this living sound. The red-winged blackbird, one of the most common wetland birds in North America, produces a sharp, liquid call that sounds almost like water itself. The male perches on a cattail stem and sings with his bright red shoulder patches flared wide. He is claiming his patch of marsh. He is telling every other male that this particular stretch of reeds belongs to him. And the females listen carefully, choosing the males who hold the best territories, the ones with the most food, the most shelter, the most protection. The American bittern, a brown-streaked wading bird, makes a sound unlike almost anything else in nature. Its call is a deep, hollow boom, like someone blowing across the top of a large bottle. It carries for miles across open marsh. Indigenous peoples across North America gave the bittern names that tried to capture this strange, resonant sound. The Ojibwe called it a name that translates roughly to the thunder pumper. The bird produces this call by gulping air and forcing it through a specialized throat. It is one of the most unusual sounds in the animal world, and it belongs entirely to the wetland. Insects fill in the spaces between the bird calls and the frog songs. Crickets, katydids, and cicadas layer their rhythmic clicking and buzzing over everything else. The water itself adds sound too. A gentle lap against a root, the soft drip of dew falling from a leaf, the almost imperceptible movement of water through dense grass. A wetland at night is never truly silent. It is always breathing, always shifting, always producing some quiet evidence of the life it holds. Scientists believe that this constant sound plays a real role in the health of wetland communities. Sound helps animals find mates, warn each other of predators, and establish the territories that organize their lives. When human noise pollution enters a wetland from roads, from boats, from nearby development, it disrupts these signals. Frogs call at different pitches to be heard over traffic noise. Birds change the timing of their songs. The whole acoustic structure of the community bends and shifts under the pressure. And yet, in the deep swamps, in the remote bogs, in the flooded forests far from roads, the ancient sounds continue. The frog still calls before dawn. The bittern still booms across the open water. The insects still fill the warm night air with their layered, rhythmic song. These sounds have been rising from wet places for hundreds of millions of years. They rose before humans existed. They rose before mammals walked the earth. They are among the oldest ongoing conversations in the history of life, and the wetland holds them gently, the way it holds everything, in quiet, patient abundance. There is something remarkable about what happens when a wetland is left alone. Given time and space, a damaged wetland can come back. It does not need human hands to rebuild every root and reed. The system carries its own instructions. The soil remembers what it was. The seeds wait in the mud. The water finds its old paths again. Scientists call this process natural regeneration. And in wetlands, it can happen with surprising speed. When a wetland is restored, meaning when water is returned to land that was drained for farming or development, plants often return within just a few years. Cattails push up through the shallows. Sedges spread across the wet margins. Willows lean out over the water's edge. The plants do not need to be planted by hand. Their seeds have been carried by wind and water and birds for thousands of years, and they are ready. The animals follow the plants. Frogs arrive first, drawn by the shallow water and the soft mud. Then the insects come, filling the air above the new surface. Then the birds come for the insects and the frogs. A wetland that was dry and silent can become loud with life within a single season. The speed of this return is one of the most hopeful things in all of nature. This healing power comes from the wetland's deep relationship with water. Water is the engine of everything here. It carries nutrients in. It flushes waste out. It keeps the soil soft and rich and full of the tiny organisms that break down dead matter and release it back into the cycle. When the water returns, all of these processes restart. The wetland does not begin again from nothing. It picks up where it left off, like a song that was paused mid-note. Peat bogs, those ancient, slow-growing wetlands built from thousands of years of compressed plant matter, are harder to restore. A single meter of peat can take 1,000 years to form. Once a bog is drained and the peat is cut away, that record is gone. But even here, scientists have found ways to help. By blocking the drainage ditches and raising the water table again, researchers have watched sphagnum moss, the soft, spongy plant that builds peat, begin to grow back. It is slow. It is measured in decades, not years, but it begins. The fact that wetlands can heal at all tells us something important about how life works on this planet. Living systems are not fragile in the way we sometimes imagine. They are resilient. They bend under pressure, and when the pressure lifts, they reach back toward what they were. The instructions for a functioning wetland are written into the seeds, the spores, the eggs buried in the mud, the roots of plants that have been waiting underground for years. Life is patient in a way that is hard to fully grasp. Step back even further, and the picture grows larger still. The atoms that make up a wetland's water, its mud, its plants, and its creatures have been cycling through the earth for billions of years. The hydrogen in the water of an Amazon floodplain was once part of an ancient ocean. The carbon locked in a peat bog was once floating in the air as carbon dioxide, pulled down by a plant that lived and died, and slowly became part of the ground. Nothing is ever truly lost. It only changes form and moves on. The calcium in the bones of a great blue heron, standing still in shallow water, was forged inside a star that exploded long before our sun existed. That calcium fell through space, gathered into the young earth, cycled through rock and ocean and soil and living things for billions of years, and arrived, finally, in the long legs of a bird standing in a marsh at dawn. The universe built that bird slowly, over an almost unimaginable stretch of time, using materials it had been carrying since before the earth was born. And the wetland holds that bird gently, the way it holds everything. It provides the shallow water, the slow fish, the patient stillness that the heron needs. The wetland does not know it is doing this. It simply does it because that is what it is. A place where water and land meet and life pours into the space between them. When a wetland heals itself, it is not doing something unusual. It is doing what living systems have always done. It is continuing. It is finding its way back to balance, back to the slow, steady exchange of water and carbon and sound and light that has been running in wet places since long before anything walked or flew or called out across the open water at dawn. And so we arrive at the end of our time in the wetlands. We have moved through the mud and the roots. We have watched the heron stand still at the edge of the water. We have listened to the frogs call out in the dark and followed the slow drift of water hyacinth across a still surface. We have looked down into the peat and found the past preserved there perfectly, like a letter no one knew had been saved. The wetlands of this planet cover roughly 6% of Earth's land surface. That is a small share of a very large world. And yet, those wet places do more quiet work than almost any other kind of land on Earth. They filter water, they hold carbon, they slow floods, they shelter the young of countless species. They have been doing this without pause for hundreds of millions of years, long before the first human being stood at the edge of a marsh and looked out across the reeds. The wetlands were already ancient. The first land plants appeared roughly 470 million years ago, and wet environments were among the first places they took hold. The coal seams we mine today, the ones buried deep beneath cities and fields, were once vast swamp forests. Trees fell into warm, shallow water. They did not fully decay. They compressed slowly over millions of years into the dark fuel we still pull from the ground. The wetlands of the ancient world became part of the ground itself. There is something very still about knowing that. The energy in a lump of coal was once sunlight, captured by a swamp tree, stored in wood, pressed into stone over an almost endless stretch of time. The wetland held it, the way wetlands hold everything, gently and for a very long time. Tonight, right now, there are wetlands on every continent except Antarctica. The Pantanal in South America spreads across an area larger than many countries, flooding and draining with the seasons in a slow, breathing rhythm. The Okavango in Africa fills a desert basin each year, turning dry land into a shimmering inland sea that draws elephants and lions and thousands of birds to its edges. The Sundarbans, shared between India and Bangladesh, form the largest mangrove forest on Earth, where tigers swim between islands and the roots of trees hold the coastline in place against the sea. Each of these places is different. Each has its own water, its own soil, its own creatures, and yet they are all doing the same thing. They are holding the line between water and land. They are keeping the exchange going, carbon moving into soil, water moving through roots, nutrients cycling from mud into plant, into animal, and back again. The same patient process, running in wet places all over the world, all at once, right now, in the dark. Scientists estimate that wetlands store more carbon per acre than almost any other ecosystem on Earth. The peat bogs of the far north alone hold roughly 30% of all the carbon stored in soil worldwide. That is a staggering amount of work being done by quiet, still, often overlooked places that many people have drained or filled or built over without fully understanding what was lost. But wetlands are resilient. Given the chance, they return. Seeds drift in on the water. Roots spread through the mud. The slow chemistry of waterlogged soil begins again. A place that was dry and silent fills, over years and decades, with sound and life and movement. The wetland does not need to be invited back. It simply comes when the conditions are right, because this is what it does. Somewhere tonight, a marsh is resting under a sky full of stars. The water is still. The reeds are quiet. A frog sits at the surface, breathing slowly. The mud beneath holds centuries of carbon, centuries of fallen leaves, and slow decay and patient accumulation. The roots of the cattails reach down into that dark softness and hold on. Above it all, the stars are very far away and very old. The light reaching that marsh tonight left its source long before any of us were born. And the wetland sits beneath it, small and wet and full of life, doing its quiet work the way it always has. The planet is large. The universe is larger still. And somewhere in the middle of all that vastness, a small, wet place at the edge of the water is holding things together gently in the dark. Rest now. The wetlands are still out there doing what they do. You do not need to watch over them tonight. Subscribe for a brand new Earth topic every night. One tap, and something wonderful is waiting for you tomorrow. Sweet dreams.